Okay, good morning, students. This will be our first lecture on Mechanics of Machines 2 or ICN 202S. I'm just gonna, this small introduction, just what's expected of you, what we're gonna cover, and then we can actually get onto the so-called nitty-gritty of of the subject. It's a fairly challenging subject. Concepts can be difficult to understand at times. However, I'll provide sufficient support so that you're able to understand these concepts. And usually I want to have a fairly long, but an introduction with regards to Newton's first law, second law, third law. So you kind of get your mind back into it. But I decided, okay, I'm not going to really focus too much on all of that. Anyway, so just to go through the slides, that's me. Now, you guys are with the lectures, right? So this is nothing new to you online, right? Yes, prescribed textbooks for this particular subject. So if you look under content under Blackboard, I've basically uploaded each chapter of the notebook to individual forms. However, I've printed out the notebook, so I've printed around 60 copies, and you guys will be able to collect it. I'm not sure exactly when, hopefully this week or next week. So it'll be a notebook of all the notes essentially. So that's our main textbook. So it'll be a notebook. So it's a fairly, I guess it's an old notebook, but it does its job. I'm also going to be using another textbook with Theory of Machines by R.S. Khurmi. I'm not sure if you guys are familiar with that book. And that's a secondary textbook with extra examples. For instance, there are things like centrifugal force, which is not covered in the notebook, like a governor. I'm sure you guys will hear a governor, like a watt governor. And so things like a governor. So there's like, I have extra notes basically from that textbook, which will be incorporated into our syllabus. Then also we have these other textbooks, which is the old faithfuls, and one new textbook. But this is the one on top here, basic engineering mechanics. That is my ex lecturer, and I'm using these. But like I said, anything relevant. Basically all these extra textbooks are just small sections which will accentuate the main textbook. So you just take it as one body of work, but the notebook is exactly how we're going to be kind of following the syllabus. Next, okay, so this was initially planned. This plan has changed, obviously, due to this subject starting late. So, but what we're going to be looking at essentially for the first term is inertia and in accelerating systems. We'll be looking at relative velocity, centrifugal force, mass moment of inertia. The mass moment of inertia is a very important concept because it's the central standpoint where all the other concepts like simple harmonic, mass moment of inertia application, belt drives and brakes, clutches are all kind of built up from. So the schedule is of course not correct anymore. However, if I look at exactly, if I'm looking at a timetable, we should be able to cover this 4 sections as planned, because not all of them is big, right? And some needs a bit more time than others, but it should be enough time. Now, I was going to pose a question to you before I actually continue that schedule. I'm going to paste the S3 timetable. Just give me about that. I'm looking for timetable. Okay, can everyone see the timetable? Yes?
Yes, sir.
Okay, so what I'm proposing is, thank you. So what I'm proposing is to catch up with moms a bit. So what's gonna happen is that, like I said, you must probably need a new lecturer for strengths and electrodes, right? And we'll have a mom periods as planned, as per normal. But then what I'd like is to add an additional period somewhere over here. I mean, I don't know where I can actually have the period. Where would you guys like to have the extra period? I was maybe thinking maybe an hour in the morning Friday before legal knowledge. And then, yeah, I think the Friday session, the first and second period. Is there any advice for me in terms of that, just so that we have an extra period to catch up and do more work and examples? Jason, Mr. Silva, Mr. Neto.
Yes, sir. I think Friday, the first ones, it's okay for me because they are
Yeah.
empty.
Thank you, guys. Good for me as well. So you'll keep it as a flexible period. So I'll say, guys, we'll be having mom on a Friday. I'll let you know. But our core periods will stay our core periods. But you can keep it as a nice catch-up period. Because the subject requires a bit of work, and I don't want any student to be left behind. So I want to make sure I'm covering enough content. We don't want people to be, and all the subjects are prerequisites for the next level subject. So we want to make sure that that's all covered essentially. So I'll let you know by tonight. We most probably gonna have a period a lecture on Friday. But I'll post an official announcement on Blackboard just to make everyone aware of that. But thank you for that. Moving along. Sorry. Test is roughly the same, but in our case now, our first test will be on the 16th of April. So this is going to change. Where I'm here. So this test, what I've done, apparently, to you guys, so the term ends the 31st, and you guys return the 12th. So you would have more than enough time. So you have like a study break or study week or actually the break. So when you guys return in the week of the 12th, on the Friday, 2 o'clock, you guys are going to write your first mom's test. So that's just to ensure that you guys have enough time to prepare, and I'm sure the holiday is going to do you good. So we can just focus for the next 4 weeks and push the content and try to engage with as much as possible. So please, I've mentioned the other test dates. Of course, we can have 2 tests weighing each 25% each. The fees is 50%, which is moderated. Yeah. I will be sending you through the course of some past papers and stuff for moms as well. I haven't forgotten strengths to touch, so don't worry about that. I just had to prepare a few things for moms this morning, which I wasn't really happy with. So I was running with someone else's slides, but you get your touch for strengths by today, so you can practice that as well. And as in, I'll post an additional announcement for electrodes, so that you can just say, guys, in the period of this qualification, please keep on study ahead. It's not difficult at all. Moms can be a bit of a headache, but we will make sure that we try to get through it, enough practice. It's what I expect from you. Like I said, guys, make sure you complete all the exercise in the notepad or textbook. Just make sure, ask questions again. Try to watch additional YouTube videos. If you want me to get you some good YouTube videos, I'm more than willing to check for you. And I have for you for each section. So you can basically get a better perspective to have more than one teacher. Yeah, so you need to put in the work to ensure that you pass these subjects. This semester is a lot better than next semester, so if you have a good work ethic now, it's definitely going to help you for the next semester. So I'll let you guys know that on Friday. I'll send another announcement. Of course, we probably start at 9 o'clock, so quarter to just like a nice catch-up period. I try to make the lectures light as possible. Plus, then of course you can consolidate during the weekends. Fine. Yeah, test one. I think now I did mention this. So it's probably chapter 1 through 4 or 1 through 5, depending. And so you can exactly know what's expected of you. So we will start with the first chapter today, and we'll start literally in the next minute or so. So if there's no questions, guys, is there any questions before I move on to the first chapter? Regarding notes, textbooks, maybe check the class list before. It's entirely up to you. Just give me a few thumbs up so I can proceed. Students, I'm just thinking of something. Okay, great. Okay, fantastic. Okay, so guys, notepad must be collected, and then I am posting all exactly the same notes on Blackboard. Some old school notes, but yeah. I'm just looking at something here. Okay, it's fine. Right. So let's quickly, before we start, right, get you guys straight into it, some quick revision. So this is a friction problem. Treat this as your first wake-up call for moms, because this is where we're going to be starting off, and this is where we're going to be building on into a very important concept. So what I'm going to do is copy this. I'm going to give you guys around 5-10 minutes to solve this one, and then I'm going to solve it, and then this is going to be this example is going to be from where I'm going to take off this new chapter. This new chapter is essentially based on this kind of concept. So I'm just going to quickly put it on my whiteboard. I'm going to see who's still sharp with your marine science or mechanics of machines. And yeah, then we're going to take off from this example, because the chapter we're going to be doing now is called the D'Alembert's principle. I'll say it again, D'Alembert's principle, and it's the idea of inertia, or linear or translational inertia. Does anyone have an idea what inertia is before I proceed? Before we start with the example, this is a brief discussion. Does anyone have a listing or perspective on inertia? Quickly, no pressure.
We can say like resistance to move, yes, sir.
Fantastic, fantastic. It's the resistance to moving. That is fantastic. It's a good starting point. Exactly. Body resistance to motion. Fantastic. So body's resistance to motion. So now that is going to be our premise now, right? So before we start that, this is just some. So instead of me explaining in words what you must know in terms of certain concepts, what I do is just I'm going to smack you with a nice example here, and I'm going to see just to get your rust off. So I'll give you guys around 5-10 minutes. Is it fine to quickly tackle this guy? And then we'll, of course, go over together, and then we can finally talk about this inertia which I'm talking about. Right? So I'll be back. Well, I'll be here, but I'll be back in 5-10 minutes. Please try to do this quickly as possible. So basically, just what's happening here, so you've got an object resting on the inclined plane, resting, And they're saying it has a weight of 4,300 newtons and it's just on the point of moving up, right? So just on the point of moving up. So they're asking what must be that applied force. Okay, I will zoom in. Let me zoom in here. What must be the applied force basically to keep this guy in equilibrium, right? So it doesn't move. So let's find these forces, right? Zoom in. Yeah, so a fairly easy example, but just important for you to, I want to see if you guys remember how to split the components of weight then, things of that nature. All right, there we go. Are we winning over here?
Yes, sir.
All right. I think I will. How do you guys manage? I think I will come on to this one. Let's see. Okay, so first things first, very important concept in mechanics, guys, your FPD. You guys are aware what the FPD is, right? Your free body diagram. So what's important of a free body diagram is that we need to identify all the forces, as you know, acting on the object, right? Okay, so in our case, we've got, I think I should sketch it rather here. We've got our block here on a 30-degree slope here, right? Maybe someone's trying to pass their drivers. Well, maybe 30-degree slope is a bit generous, right? And we know we've got the body's weight acting downwards, right? But the weight is now split up into two components. I'm not going to sketch the actual weight, but we are aware of the mg sine component. And I'll include the angle 30 degrees. Of course, we have another one going like that, which is mg cos, right? Cos 30. Okay, so I hope you guys all get that. Of course, we've got the knowable force here, right? And then in this case, we've got the force here, but this force, what I'm going to do is split that force into oh, should I get that nicely? I think I'm the first sketch the force with the other color before. I'll just have it like this. Just say like that. The so-called of, so as I say here, it's on the point of moving up, so it's like nearly equivalent. So of course, this is going to be ft cos. Are we all familiar with this? And we've got another guy here at ft sine 30, and that's your normal force. So if you guys remember, also because it's on the point of moving up, we've also got some static friction happening here, right? And the static friction is, we denote it normally F mu. So I'm saying this is all the forces on my body. Do you guys agree with this? Who is not in agreement with this? Can we have a small debate? We'll be doing, the first chapter is solely based on this kind of concept. Are we all happy with this? Does anyone disagree with this? I hope you all got the same kind of. Yeah. Okay.
Yeah,
right.
I agree.
Thank you very much. Okay. So, what is the first thing we do, right? We essentially do, is it the third law of Newton's over here? And it essentially is all forces, it's a symmetry law, right? And of course, if there's a force, so if for every external force that acts on an object, right, there is an equal magnitude but opposite direction. But in essence, what I'm trying to say is that we have to sum the forces in the x direction and in the y direction. I think I'm right here. So what do we have here? If I sort this out, because our objective is to find this just applied force, the force just to keep it on the point of moving up. So I'll say ft, right, cos 30. There should be, of course, a ft subscript t, cos 30. So that's positive, right? So we all know, we assume that to the right is positive. So where this all comes from is your x. Everything is essentially in a Cartesian plane, which I'll talk about, right? And we know that this direction is positive here. In fact, it depends on also how it's moving. Isn't it cos 15? Oh, thank you, but sorry about that. I nearly sabotaged my calculations. Thank you. Is cos 15. That particular load is at 15. So just forgive me for these ones here. Yeah, thanks. Okay. Cos 15. Okay, we're all happy with that. So cos 15. In the x direction, we've got a negative mg. So we've got the weight, not the mass. 4,300 sine 30 minus mu, and of course 0.5, 4, and then this will be n. So we're all aware that the friction force is, and I'll write it over here, F mu is mu n, right? It's a function of the coefficient of friction and the normal force. This will be equal to 0. So for us to resolve this, we're going to need n here, right? But then now we have to look at the sum of forces in our y direction, and this is where n actually is, right? Hopefully we can solve this, I hope. So then here we're going to have n plus ft sine 15. That's going to be equal to, or I can say negative, obviously, if you guys like. I'll say negative. I'll just say negative rather. What's mg here? Mg is off, so it's 4,300 cos of 30. Okay, that equals 0. So we're having a look at this. What I see is two equations, two unknowns, right? And that's how we're able to solve for ft. And the way we're going to do that is, of course, sort this all out all nicely. So we can end up with a simultaneous, well, we can solve by matrices, which that's my approach, or by substitution. So for equation 1, I'll say 1. I'm just going to call this 1 again. It's going to be ft cos 15. Oh, I'm going to say minus 0.54 n, and that's going to equal to whatever that value is, positive 4,300 sine 30. Right, so you get 2,150. For the next equation, so ft sine 15, that's going to be plus n, and that's going to be equal to positive that value. Yeah, because that's going down. Okay, right? That's minus, well, it's 4,300 now, cos of 15. The cos 15 or cos 30, sorry, cos 30. And that gives me 3,723.91. Two equations, two unknowns. What I do, I open up a matrix. We can do this by substitution, of course. So what about the gravities for mg cos? I'm not with you. Oh, I see the gravities. Sorry for the late results. Oh, remember it says here in the question. Oh, I understand. It says it has a weight of 4,300. So the mg is given to us already. Are you with me? Remember, mg is in Newton. Weight is in newtons. I don't know if you agree with me there. So you can do this by substitution if you want. So remember, so weight equals mg, and if you were to find the mass, you'd say 4,300, assuming that we're on Earth over here, not in Mars. We can find the mass of the object, right? That's if you want another mass. But of course, they give it to us for the ease of the calculation. So here we have cos 15 minus 0.45 sine 15. We have 1. This is going to be ft. That's going to be n, and this is equal to 2,150.37 2, 3, 9, 1. I'm hoping I did everything right here in terms of my forces. And yeah, we can get what FT is, and then I like you guys to give me these answers, please. I don't want to work this out. Just a warm-up example so that you guys are aware of how to play around with this kind of stuff. I like to use matrices instead of using simultaneous equations. But of course I can, and I'm just giving you grace by not actually working out. So if you're smart, you would have gotten this answer here. First law of equilibrium. Yeah, is everyone happy with this? If you have any questions, please ask. Right. It's a very important, how does one say, this is what we're doing here. It's very important for this chapter. So I just want to start with the fundamentals prior to, before I start. So now mechanics was a bit of a rough subject for some people. Is everyone happy? Can I move on? Is there any questions pertaining to this? Please ask. Do not keep it in. Questions? If you guys are happy, just give me a few thumbs up so I can move on. People are awfully quiet. Thank you, Pauline. Thank you, Pauline. Ah, Mr. Abriel, expert. Remember what the question states. What the question states. But this is what the question states. I'm just on the point. Okay. Question states. Hey, where am I? Says just on the point of moving up on the plate. So we're assuming it's stationary. Okay, so you're all happy with this. We can go revert back to our slides now, and that's what take us. Okay, back to the slides. So I'm not sure exactly what you were taught in the previous in mechanics. This is like a revision chapter itself, because normally it's taught there. So as Mr. Abriel said, right? So this, we assume this body is equilibrium, meaning that it's not moving, it is stationary, no other forces are acting upon it. But what's going to happen, and I'll hear from you guys, if this body, let's say for instance, like if it had to actually move forward. So let's say, so it moves forward. Yeah, okay. So if it moves forward, what is going to happen, right? So just talk to me in terms of the horizontal forces here. What is going to happen? So of course, we know that what we have here, we've got an F mu here, right? Frictional force. Is that correct? But as we move up and it's accelerating this way, it's accelerating forward. Mr. Silver, tell me please. Something's going to happen. It's moving, we're accelerating at say 3 meters per second squared. This is a very thick coke here, guys. Sorry about that. I mean, you guys kind of already know the answers. Seems. Oh, lost signal. Mr. Abriel, tell me what happens. We have the inertial force, right? Do you agree with me? Guess no one thought about that. We've got a force because of the mass of the body. There. Call it Fz. You guys familiar with inertial force? The inertial force. Are you guys familiar with it? That's
Yes,
chapter
sir.
covering. Okay. Other students, Brent, Tommy, are you guys aware of it? Mr. Zuma, Puleng, are you guys aware of it? Tsepo? Oh, you guys are aware. Fantastic. So you guys did cover it. So to touch back, to continue the actual lecture, right? So a few backdrops before we touch on the inertial force. And I'm just following the kind of note back train of thought here. It says motion, right? So this is kind of just breaking away from what we just touched on. So they say motion, say that your motion contains two primitive concepts, right? It's position and time, right? So we're familiar with time. Now, what I want to elaborate here is on position, and they say if we are to specify the position of a point of an object on a line, we must agree on an origin, where it starts, the line, and the sense of positive direction. So this is things you're familiar with. And the reason why I'm talking about is you're going to see exactly where it's all coming through. It's just all going to reach onto basically inertia, right? So we agree on position, right? You know, a 0 point on the line it's moving and what is positive, what is negative, right? Okay, so what's important is that now we locate the point. We use something called a Cartesian plane, a two-coordinate Cartesian plane. Now, of course, what we're supposed to be learning, and this is more an advanced concept later on, would be a three-dimensional plane because we live in a three-dimensional reality. But for our sake, we're only dealing with our x and y. So this will be our reference system. So that point and that line is positive and negative. That's how we allocate position. And so if we are to specify uniquely the position of body in space, we may do this by noting its distance from three mutual perpendicular axes, which will take as a fixed reference system. It's just essentially the day using the Cartesian plane to reference of power points moving. Of course, we'll be using two in this case, right? And also, it's very important. This motion, right, is relative, and we'll touch on in the next chapter on relative velocity. That is relative to the Earth itself. And of course, we know that the Earth is not stationary, the Earth is rotating. So, but what we assume on Earth, or basically our primary reference here, they say, is the average motion of the stars, apparently. So, we know the Earth rotates around the sun, I think. And so the idea is that we are not relating that motion. So, we assume that the Earth is stationary, and we're adopting a Cartesian plane reference system for things to move, right? And which we kind of been adapting for the last. So we talked about the position, right? But we know position is a function of position and time. Talked about position and time. Sorry, we talked about motion, and it's scatterized by position and time. So motion itself, and of course, at its most primitive and basic form, is classified into two kinds. It's translational, which I'm going to call here for you guys linear. If you want to be fancy, you can call it translational motion. Right? And then the other one is rotational. Now, we in this particular subject want to do a lot of rotational problems. Everything will be rotating. Why do we concern of rotating? As a marine engineer, mechanical, most of our systems are consistent of rotating elements. Gears, belt drives, shafts, flywheels, governors, things are spinning. So we want to understand what forces, what dynamics are within those things. And this is what the subject is going to unpack. Right? Look at two kinds of motion, translational and linear. What is translational? Translational and rotational. What is translational motion? Motion called motion of translation, or simply translational, that sounds bloody confusing, is the axis of a coordinate system imagined digitally fixed to an object, always remain parallel to the some fixed coordinate system. One example would be a piston moving back and forth. That motion of the piston moving, right? We're not talking about connecting a rod, the crank. Yeah. We're talking about it moving up and down, is rotation. So what they mean parallel? So if you could imagine a fixed coordinate. So we assume a fixed coordinate system, x and y. And as it's moving from A, B, and C, you've noticed it stays exactly in the same position. It is not moving. That's what they say here. Imagine rigidly attached to an object always remain parallel to the axis of some fixed coordinate system. So that is, I guess in mathematical terms, what linear motion is. right? It looks, it just moves, it doesn't change. The axes don't change, right? What is rotational motion? Motion is called rotational. The axis of the coordinate system imagines, which is imaginary, we attach it to the object again, does not remain parallel to the axis of the same fix. So what we're saying is that this one remains parallel to the fixed one. But in this case, can you see how that thing is spinning? So if you look from S.Chand K, this particular object, X and Y, is moving all over the place. And if it does that, that is deemed rotational motion. Right? Examples here. There's so many examples. There's a revolving flywheel. That doesn't look like a flywheel to me. I'm not sure exactly. It's like a pipe wheel. But it's continuously rotating. However, what's important to note, a body may experience both translational and rotational motion. Now, you see this with the car driving its tire, right? Even though it's rotating, the car, it's actually moving forward as well, right? And so, a ball, and I give you an example, they actually do say, such as a ball rolling on a table or wheel. So that's just to understand the concept of what linear and rotational. And this is two important concepts because we've talked about this concept of inertia, right? And inertia is going to come out in both linear fashion, in a linear fashion, which we discussed today, and a rotational fashion. And what we're going to be doing specifically with a rotational one, we're going to be able to quantify the rotational inertia. We're going to give it a number. So before we start, what is translational inertia or linear inertia? Can someone tell me and give me an explanation? Quickly, Jason. Len, what is Abril? What is inertia? What is translational inertia or linear inertia? Can we talk about it quickly? You guys are listening. Anyone? Yes.
I think it is a linear inertia. I think it's related to velocity, something speed. So
Okay. Give an example of what inertia is, translational linear inertia. Just give a quick example. You can't think of one? Mr. Neto? Okay.
yes, sir.
Yes.
No,
Go for it.
no, I have no idea. Example.
Okay. It's
Maybe
fine.
I don't know. I'm not sure, but maybe like let's say like for example, a car moving around the incline, a slope, something like
Yes.
that.
Okay. Okay. I'll try to illustrate for, I don't know, I guess this is what I'm asking. So, he talked about, Mr. Abru talked about a moving piston. So, if piston A weighs 5 kilograms and piston B weighs 10 kilograms, which one has more inertia? Which has more inertia? Piston B, exactly. This is what it's about. So linear inertia is mass. What you know as mass is linear inertia, right? So what is inertia? The tendency of an object to resist changes in its state of motion. That's what it is. So the bigger the mass in a translational way, and we need to be careful here, in a linear way. So we're trying to push God knows what. I can't even think, like a car, like in a straight line. And what's resisting is the inertia of the mass. But let's say you're trying to push a not cable car, but like a smaller car, and you're pushing it, the car will move, and there's less inertia. So what it essentially is, the amount of inertia of an object depends on its mass. There we go. That's what actually just states. So just reading off, the first law states that all objects have inertia. the more mass an object has, the greater its inertia, and the more force is required to change its state of motion. Now, this does not apply to the rotational aspect. So that is something we're going to be touching on in the next 3 chapters. So what you understand for now, what you know is translational linear inertia, moving something in a straight line only, where the axes do not change. In the next one, the axes are going to be changing, and therefore we have to quantify new things. So at least with inertia, we know how to quantify it, and we quantify it in kilograms, right? If I weigh 100 kilograms, I got more inertia. If you weigh 25, then you have less inertia. Linear inertia, sorry. Okay. Moving on. Small example here I found off the internet. It says you can tell how much matter is in when you can kick a can. Okay, that is the only thing of matter, but the idea is that if you kick an empty can, it moves, flies pretty easy. If you kick a can full of sand, it doesn't move as much, right? Obviously. So one is more inertia than the other. That's just a small idea. What do you think happened here? They say your truck has brakes, but the massive hunk of stone doesn't. So this guy drove. He brakes. We're not sure why. What is that thing there? That extra force. You know that force? It's inertia. Right? What's the definition? The tendency of an object to resist changes in motion. Right, okay. That's one case. Here we go. What's happening there? You know, it's getting Newton's laws for that inertia force, that mass. Another small example. And in bumper cars, right? You know, when you're knocking each other, there's a force, an extra force. There's a resistance. There we go. Okay, so we've played around with what inertia was. Says inertia, force. Okay, yes, here we go. Force is the physical phenomena that changes or tends to change the velocity of a body. Right? It's defined as mass times linear acceleration, of course, linear. And every object in a state of uniform motion tends to remain in a state of motion unless external force is applied. Fine, we're aware of this. These are essentially Newton's first laws all jumbled together. Then I say inertia is a property of a body which resists any change in its velocity. I'm going to repeat that again. This is definitely going to come to test. I'm definitely going to ask you define inertia for me. Give me a definition of mass. And what is linear inertia? What is mass? Mass is the magnitude of a body's translational inertia. That's all this thing is essentially about. So if you understand this, you're on a good note. And this is going to tie into the other chapter where we deal with rotational inertia. That is why we started with inertia in this particular chapter. Right. Hope everyone's happy. So now we go on to the Allenby's principle. A very basic idea, right? So I'm gonna probably just have to go back. I have to probably sketch on this slide over here. So just reading off here, the idea, it's a basically simple thing. I see a consider a rigid body upon a system of forces, which a system of forces is acting upon. The system is reduced to a single resultant force acting upon the body, whose magnitude is given by the product of the mass of the body and the linear acceleration. All fancy, but what essentially means if I sketch on this guy, we've got a force going this way. So Ft or F applied doesn't really matter. We can call it Ft. Something's going to resist our motion, and that is the F. We're going to call it the Fz force. This itself is the Allenby's principle. Of course, there's another guy I've also talked about it. So that's all it really is. So it's additional force when the body is moving, besides the frictional force, obviously. Let's say a little consideration will show that if the quantity MA may be treated as a force, right, equal and opposite to the line of action. So what's important is to understand it's resisting the motion. Where am I here? So in the same line of action as resultant force F, and include this force of the system of forces of which F is the resultant, then the complete system of forces will be in equilibrium. So the idea is, of course, equilibrium because it has to balance out. You know, everything in life is symmetrical. So we apply forces on that one side, we're getting resistance on the other side. They're equal to each other. This is called the Allenby's principle, right? The equal and opposite MA. I think we touched that. People did touch this in high school. That is the inertial force, and we'll be calling that as Fz. The principle states the resultant force acting on a body together with the reversed effective force or inertial force are in equilibrium. You get the idea there. So that's all it essentially is. So just as this is from the actual notepad. So we're just talking about this. This is all the conditions for equilibrium you're applying, and one is the algebraic. We have two conditions of equilibrium. I hope you guys know it. The algebraic sum of the forces acting on a body is 0. The second one is the one of moments. Second condition for equilibrium, the algebraic sum of moments on the body at any point is 0. So moments equals 0. So we apply the Ellenberg's principle. We use the inertial force Fz. Of course, we call it something else. We're just using Fz, and it's always opposite. Remember this, because when we're going to be dealing with rotational systems, it will apply exactly the same thing. So what they have over here, they're explaining on the small schematic. So if this body was initially in equilibrium, it's standing still, right? You've got your weight acting down, right? We've got this guy, which is equal to your normal force. If you agree with me, right? N is mg. Then we've got a frictional force. So we're assuming applied force is going this way. So we're going to call it Fa. And that's also, that was resisting the F mu force, right? That's just in that static equilibrium standing still. However, now we start to accelerate this body. We just go with the green force. So I'm just essentially explaining a small box, a small thing. You're going to get another force on another side, which is the Fz. Right? And then, of course, you apply the conditions of equilibrium, and then we can balance out the forces, and then we can make everything work nicely together. That is the idea there. And then we can solve for whatever we need. Acceleration. So it's exactly the same as a frictional problem. And of course, this is a horizontal rough surface. So if the important note here, and it says the Ellenberg's principle applies to equally to torque, which produces angular acceleration. This will be taught fully later on in the course. And this is very important to understand. So there will be two examples. So one example would be you've got some kind of hoist lifting up some masses, and if it's rotating, the torque is going up. We have a clockwise torque. Yes, we do. We've got this rotational inertia, right? And this is quantified later on. So I'll just give you a small hint just for future. Do you remember in linear motion and angular motion you had your V equals, you remember this? Then you had a correspondence omega 1 0, you get the idea, alpha and T. I'm just going to drop this nicely with you. So here for linear, for translational, we have F equals ma, and then we become big girls and boys, torque, because torque is a big element of rotation, we're going to have something called I and alpha. And this I is the rotational inertia. So I'm just dropping the bomb there, just for now. And you can see, if you look on the diagram to the right, there we have some round body rotating up a slope, right? I don't know if you guys can see that. And as you can see, so it's rotating downwards. And if you actually, not only we have the linear counterpart, we also have the inertial torque. We have inertial force and inertial torque. So that is where it's all going to boil down to essentially. So I want you guys understand, this is just a warm up or introduction. So when we touch on this concept at a later stage, you guys are aware of the extra force to rotate the object. You thought it was simple, it's not. Welcome to S3, welcome to Mechanical Machines 2. All right. So what I want you guys to do now is try example 1 for me. I'll give you guys around 5 minutes, 10 minutes. And remember, we're in a realm of dynamics, things are moving. So I'm going to give you guys a small attempt of this with example 1. We do example 1, then I'll do example 2. So I'm making sure you practice all of this as we move along. This is also this definitely be one question in the test, the inertial thing. The test will cover inertia, relative velocity, centrifugal force, and mass moment, and maybe simple harmonic motion. So what I'd like you guys to do is try example 1 for me, please. Thank you. I'll give you guys around 5-10 minutes. Then we'll do example 1, 2, and I've got, I think, 4 examples in total which I want to cover on this particular section. Okay. Thank you. I'll see you guys in 5 to 10 minutes. Please try number 1. Fantastic, Mr. Key. Did everyone get the answer? Did everyone get the answer? Should I attempt it? Can I go for it? Students, are you still there? Oh, fantastic. Do you think I should still do it? Oh, must I? Okay, yes, please. Okay, let's do it. I'll share my blackboard with you, and then yeah. So we do quite a few of the examples just to get you back in mechanics. With the next session, well, we'll probably be starting with relative velocity, I guess, or we might continue. Then I'll see. It depends. I don't make any promises. Okay, so the first thing, and this is also in your notes. You can go have a look at your notes. We've got a horizontal body, right? And it's flat, not on the incline, no additional forces, right? Always start with the free body diagram. I'll just use red. And say it's moving, it's put along surface. So we just assume that it's going this way, maybe accelerating this way, accelerating that way, and it's got a pull force of 150 newtons, so that is causing the motion. And then we have two forces, F mu, we've got Fz, and of course we have our weight that goes without saying, and we have our normal force keeping that guy. The force is acting on this body, right? Okay. So they want, what do they want? They want the body's acceleration. So looking at what I normally do, some of the forces in the horizontal direction. So I think I'll just make it smaller. I'm not sure why it does this. Okay. Just a little bit like that. I think that's how we're going to start off, right? We know it's going to be force P. I'll just use force P for now. Right? Maybe I should just call that force P. That's going to equal Fz plus F mu. Right? P is 50. Our inertial force. What's our inertial force? It's mass. Do we have the mass? Yes, 10 kilograms. Oh, we're looking for the acceleration plus mu. On the surface, we have 0.2 times the normal force. In the normal force is essentially mg, if I'm correct. So that's going to be 10 times 9.81. One unknown over there, so it's going to be 50 minus 0.2 times 10 times 9.81 divided by 10. And if you get this, your acceleration should be 3,083 meters per second squared. So the body accelerates that much. So 083? I think you guys had 083 there, yeah. 038, sorry, 038. Okay. So is everyone happy with this example? Yes or no? Please, a few thumbs up, guys. I'll make sure everyone gets this. You know, because we're building on these concepts, so it's going to 038. Yeah. Okay, let's try the next one. Thank you, Jason. Guys, always units. Be like Brent, you must always have units. And Jason there. Let's start the next one. I'll just leave it over here. So a car has a mass of 1,500 and has a constant tractive resistance. So tractive resistance, you guys remember back in mechanics, is basically summing up all the losses, talk about friction losses and all the losses essentially happening in the vehicle. Of course, it's not so easy to quantify this, but it's just basically going the other way, right? Calculate the tractive effort required to give the car a constant acceleration from rest to 50 kilometers per hour on a horizontal road. So 35 seconds, and then over a distance of 392. So what they're saying is how much force you require to move that thing, to move it in horizontal road to that particular speed, considering, assuming that all the losses is going to be 250, or force losses anyway. Let's try that example. Let's see if you guys can tackle that one. It's capable here. Don't forget the inertial force. I'm sure it's going to be there. So where do we where do we Okay, I'll have a look. Of course, you're not worrying about resistance over here because it's considered inattractive resistance as well. I get 850. Maybe you guys are running off, maybe. My answers are fairly close. You guys is way out. It's close enough, but I'd like to see what you guys did. Does anyone agree with it? Okay, can I go for the students? Can I go for it? Thank you. Right, so just gonna move him along here. Fairly easy example. It's gonna get more fun soon. You've got a car on a horizontal road. Um, okay, it doesn't really matter which way it's going. Let's say it's going this way. So they want the force required to move this car in a particular direction, and here we have force. We have the tractive resistance. Of course, I mentioned to you the tractive resistance is it's the sum of all the forces reacting to the movement. But then, of course, this is now friction and uh, um, within the bearings, the road, static and kinetic friction all over. And then, of course, we have our new F set, right? So what they want is the effort. So the tractive effort is this guy, right? The effort to move this car, given that the car has a constant acceleration, very important, from rest to 50 kilometers per hour, right? So this is maybe you on some road moving a Toyota Taz maybe, and I want to know how much force you actually need to put forward. So the first step you need to do, right, is to look at your forces, which I've done, and we know that the Fe is going to be equal to F retractive plus your inertial force, right? So someone's saying something here. Okay, 844. It's probably the rounding off here. So we're looking for this Fe. So Ft we have tractive, so it's 250, and of course our inertial force here, right? So that's 1,500. And then we need its mass times acceleration, then A. So what is A, right? So we have to go to our old school Newton's laws of motion, and we can use V equals U plus AT. The velocity is, of course, we have to convert this now into 3 meters per second. I hope you guys can do that. 13.89. That equals U is 0 because it's from rest, plus we're looking for A and in 35 seconds. So if we simply get this, we should get 13.89 divided by 0. Not sorry, by 35. I got 0.3968. 0.857 meters squared per second, which looks good. Someone said something. Oh, 0.396. Okay. So if I just simply all I have to do now is take that guy. Wait, where am I? So I can remove this, put this in here. 0.39687. So I just put in my calculator, so I don't have to rewrite it again. You should get, oh, some reason I also get 845. Funny enough. Oh, I see. Oh, 845. Okay. 845, yeah. 0.28. So yeah, it's definitely right, yeah. Don't know how I got 850 in the first place. Oh, probably I had 255 here. Yes. Yes.
Isn't constant acceleration normally 0?
No, that's not true. That's constant velocity.
Okay. Okay, that's what
Constant
I.
velocity means, yeah, constant velocity means, what they mean here, Mr. Silver, is that we're not accelerating constantly. It's just that we're applying a acceleration at a constant, like, I'm thinking of, you do drive around, right? Just as a starting point. Like you're not accelerating too much, man. Just slowly at a steady state. But constant velocity means,
A is equal to 0. Okay.
yes, that's correct.
It's been a while, sorry.
No, it's fine, it's fine. This is the reason why I actually did this. Oh, there we got the question. So to go from kilometers to hour, kilometer per hour to meters per second, sorry. You take your, what's your speed again? 50, and you simply divide by 3.6, and then you get meters per second, which in this case 13.89. I think if you, what I'm looking for here, yeah. Do you get that? 3.6 is the magic number. You'll be using it for some time, yeah. Okay, I'm happy with this. It's close enough. So when you like a question like this, which probably never come in, but you probably get a mark. Yeah, yeah, and yeah. 1, 2, 3, 4, 5 marks. Just as an indication. Something like this. This thing is not listening to me. So let's do the next one. Who's got B's answer there? I think, you know what, if you change this tractor resistance 255, then you actually get the answer in the book. But it's fine, this is still perfect. I'm not concerned with answers anyway. So the next one, over that distance of 392. So we're going to have exactly the same, so this is A, B. So we're going to have exactly the same setup here. What is this? FE equals FT. Oh, I'm doing like FE equals 250 plus 1,500. And then we're going to have the acceleration, but our acceleration has to change, right? Over that distance. So how are we gonna find this acceleration, students? Can you please tell me? Which equation do we use? Which law of motion?
We can use Torricelli, sir.
Sorry?
We can use V square equal to V0 square minus 2AS.
Beautiful. Okay, guys, get me that acceleration. There we go. This is what you need. You have a new acceleration condition now. Very interesting. So for the students who haven't worked it out, you can work that out. So can you see how nicely tied your friction and your so-called rectilinear motion is coming together? And this is going to apply exactly to the torques and your angular motion formulas. It's going to be exactly the same. Ideally, this chapter session should have been covered before then, I guess. But yeah, it's just that this is the flow of the books. I'm actually just continuing with that motion. So what is my new acceleration? Hey, sorry. 0.25. I get 0.246. Guys, we can't be working with 2 decimal places here, at least 4. No? At least 4. And I've even discussed that, and that's very bad of me in terms of significant digits. 0.2461 meters squared per second. Right? Keep it to 4 decimals. So what is my new force in that case? .619. Right? So
Sir, you're just making
Yes.
a mistake. You're making meters square divided by second. It's meter per second square.
Meters. Sorry, man. This is not. I'm thinking about bloody absolute viscosity. Sorry. Thank you for correcting me. It is meters per second square. Thank you. That is now fluids.
619 as well.
Yeah, great. Okay. It's fantastic. There's no questions with this. So what we're going to do now, right? So we're going to have, I'm going to give you guys a particular, no, wait. I'm going to give you guys a problem to work through. And then, so we're going to have, let's have a break early so we can end off much more early as well. So maybe we should return at around 20 past 1 instead, right? Let's return at 20 past 1. And would you guys like to give you a practice example during the time? Let's break early so we can finish off earlier. That's what I'm trying to say. But I wanted to actually touch on an example. Okay, it's fine. Let's get back to an example when we return. So in our second session on. Yes, Charlton. So don't want to overload. Charlton. Okay. Okay, guys. So let's return around about 20 past 1, and we'll continue the Allenbert's principle. And then after that, we'll probably do I think 2 or 3 examples, or maybe just 2. And after that, then we can maybe touch on relative velocity. But I'll see. But relative velocity, if you have a period on Friday, we might start it there. So okay, guys, let's have a break. So 13:20, or make it 13. Make it, what's it, 45 now? So it's 45-minute break, which must be fair. Yeah, to 13:30. We have enough time to we will need around about an hour to finish up. Okay, thank you very much, guys. I hope you enjoyed the first section of mechanics of machines.